can, the verifier eventually will get a proof that says that commitment of the first number and the commitment of the second number will satisfy the relationship, the inequality shown here. So the prover will first generate the commitments, and then the user will submit a challenge, and then the prover will have to generate a proof based on the challenge to show that two numbers are satisfy this relation. So this will be used as a building block to prove comparison-based query results and also to prove completeness. All right. So for max verification protocol, the setup is exactly the same as before. The data owner generate commitments, sign the commitment. Now, if the query is a max of all the salary, 80 is returned, along with the commitments, the signature, and also R. So the user will have to verify 80 is actually greater than or equal to the rest of the data entries. And to do this, the user will essentially go through multiple zero-knowledge proof to get the assurance that 80 is greater than each individual data elements. And this proof has to be carried out between the user and the service provider. And it has so there are interactive proof protocols. That means the service provider has to be online and have to engage in the challenge response process. And there are also corresponding signature schemes. So essentially, the service provider will compute the proof once and for all, and then give it to the user for verification. So as you can see, without actually knowing the inputs, the user will be able to verify the query result. Again, this protocol does not reveal, does not try to hide the query results themselves. So if the user queried the max, the user will get the max. So this is a sort of a general property of all the privacy-preserving protocols. You cannot hide the user from knowing anything. And also the user will be able to infer something. For example, the user will know, okay, the others will be less than 80. And that kind of inference knowledge we cannot prevent the user from gaining. So now for the completeness verification, I'm going to present it in 3 examples. The first one is very simple. Again, completeness means that the queries that are selected are the complete set of the selection. Those are not selected must have violate the selection clause one way or the other. So if you think about a very simple query, average age of employees who are younger than 37, now you have 4 data entries. The last one is older than 37, so that is not selected. To prove the completeness, what you can do is just to show that the value that are committed in the last data entry is greater than 37, without even revealing what the value is. And then the rest of them are aggregated together. So this is a simple example, only has one attribute. If there are multiple attributes, how do we do? Consider this. If the selection is done on the age, but the aggregation is done on the salary, we can essentially do the same thing. We'll aggregate the salary and then prove that the last entry is beyond the selection range. Then for a more complex case, we want to do a selection over salary, an aggregation over salary. However, the salary is not the way that Merkle hash tree is arranged does not corresponding to the sorting order of the salary. So you can see that C65, C50, C70, and C80, they corresponding to the commitments of the salary, and they are out of order. So that's why we use the index. In this case, we'll have the index of the relative ranking of this data record hashed together in the Merkle hash tree. And then in this case, we can prove that the last data entry 80 is beyond the selection range, and then 80 is the immediate element that beyond the selected element. So the 80 is just the next element greater than 70. And this is proven by showing that the index of 80 is greater than the index of 70. So you show the order by proving the index. And then we can use the zero knowledge proof of greater than relation again. So you can prove the order of index without actually revealing them. All right. Any questions, concerns? No. So essentially, this is the way that completeness is proven here, and you can see we can handle quite complex queries. We consider multiple attribute queries, and essentially we can also generalize this to nested queries. If you consider max over average, you just go through the average proof as we've shown here, and then you have the commitments of average results. And then based on those, we can carry out another round of proof for the max. Okay. So,
Can I ask a question?
Yep.
Could you go back to the slide where you have the zero knowledge proof for the max?
Okay.
So, if I understand this correctly, then when you send the commitments at the end, those aren't multiplications in step 5, right?
You mean at the end?
Yeah. So what you're not only disclosing the maximum, but you're also disclosing how many elements are in the table to begin with.
Right. The user will know how many people in the database record. Yes.
So it's not really zero knowledge. It's it's not revealing a lot of information, but this could be useful, especially if you use that with other things. Like before, you're trying to show the index numbers were not bigger and hide that information. And it's quite possible I could use this information over a series of queries to figure that out.
Well, I think I understand your question, but let me clarify it. So as you can see, that the commitments values are actually reused, and the model does not actually, the current model, we do not aim to solve this, what we call unlinkability issue. So essentially, once the user submit another query, if, for example, the commitments of 65 will get back to the user again, the user will have some knowledge of this particular data entry, even though the user does not know it is 65, but the user knows it appears in multiple queries. So for example, if you say, give me the employee who satisfy a certain selection criteria, and